Thanks for the opportunity. Today, I will present my recent works. First, I'm Jinyi Yang, postdoc at Stewart Observatory, University of Arizona. So today, I will present my recent work about using a new reionization-era quasar sample to constrain the IGM evolution. So first, this is a typical quasar spectral at redshift around 6. As we know, we can see a series of absorption features in the quasar spectra that providing us with information of the IGM at the early universe. And we can see, for example, the lemma alpha, lemma beta forest, and to high redshift, we can also see the Petersen trough. And we can also see the near zone just bluer of the lemma alpha emission line. As we know, if the neutral fraction is high enough, for example, to high redshift, we can also see the quasar damping wing absorption feature. Now we can see the Petersen absorption extended to the right side of the lemma alpha emission line. And this is a simulation, and we can also see the observation, the spectral. This is a real spectral of redshift 7.5 quasar. Currently, there are already 2 quasars at redshift above 7 have similar measurement. We can see the obvious absorption here. That's the quasar damping wing. So what I want to do, my work is based on a new quasar sample from our new redshift 7 quasar survey. So we have carried out a redshift 7 quasar survey and have already discovered more than 35 quasars at redshift 6.3 to redshift 7.6. We can see this distribution here. So all the red points are from our new survey. And more details will be shown in figures talk tomorrow morning. So after we build up a large sample of the high redshift quasar, the reionization-era quasar sample, so what we want to do is to use this quasar sightline, high redshift quasar sightline, to investigate the IGM evolution at redshift about 6. So that including 2 projects. And the first one is using this quasar sightline to study the IGM optical depth at redshift 6 and above. So I'm using 32 quasar sightline, including quasars at redshift 6.3 to 7. And I'm taking a deep optical spectroscopy of these quasars, and we get this quasar spectral showing these 2 figures. We can see these two figures, and our quasars shown here with the name showing right from our new survey. So we can see our survey have already contributed a lot to the sample build-up. And based on these 32 sightlines, the first thing that I can measurement is the lemma alpha effective optical depth. So here, this figure show the this is a measurement from previous works and predictions of the lemma alpha effective depth evolution from redshift 4 to redshift around 6. So we can see these points over the lower limit. They're from individual, the measurement of the individual quasar sightline. And we can also see the blue open squares here. They're the mean measurement of the optical depth. And we can also see the these 2 lines, the green line. This is the best fit evolution model for redshift below 5.5, and also the prediction for high redshift evolution. So this is what we currently know. What I want to do is, since we already built a high redshift quasar sample, and using this high redshift sample to investigate, to constrain the lemma alpha effective optical depth at redshift higher than 5.8. Higher than 5.8. And based on our set line, this is what I obtained. This is the orange point here. Is from the measurement of the lemma alpha effective optical depth from the individual sightlines. And we can see our sample at the redshift range of 5.3 to 6.5. Although at redshift higher than 6.1, more than half of them are just still a lower limit. So based on the individual measurement, our result is consistent with the previous studies that about the large scatter of the optical depth at redshift about 5, which has already been suggested to relate to the inhomogeneous reionization process. As I mentioned before, at redshift higher than 6.1, we can see more than half of them just lower limit. That's due to the high neutral fraction there, and also at this redshift range is also limited by the data quality. So to improve the signal-loss ratio of our data, and also to reduce the contamination from the skylines, so I did a stacking of the 1D transmitting spectrum. I just stacked over 1D spectrum from our sightlines and get a stacked spectrum, and just measure the effective optical depth from the stacked one, and get this the orange open circles. This is the measurement here, and now we get a good measurement around redshift 6. And so we can see we have already improved the measurements at this redshift. And also based on this measurement from the stack spectra, and also combine the result from Eller's 2018, and we get the best fit evolution model at redshift 5.3 to 6.1. This is a solid orange, this is a solid line here. And we can see this one is consistent is within uncertainty at the redshift about 5.8 with the prediction of the green line. But to higher redshift, we still can see a redshift higher than 6.1, we still just get the lower limit. This is affected by the high neutral fraction, where lemma alpha transition may be saturated. So in this case, we need an additional tracer. So that's why we use, I'm using the lemma beta forest, which is more sensitive to the high neutral fraction IGM. So using lemma and beta forest, I'm using the same way to measure the effective optical depth from both individual and the stack spectra. I first measure observe the lemma beta effective depths, and then convert the lemma beta one to the lemma alpha effective depths by subtraction the foreground lemma alpha absorption, and also applying a conversion factor between lemma alpha and lemma beta, and just in order to compare our lemma beta result with the lemma alpha result. So we can see in these two figures. But this is the left one show the individual from the individual sideline, and the right panel show the result from the stacked spectra. From both, so we can see the lemma beta forest provide additional constraint on the lemma alpha effective optical depths at redshift around 6 to 6.5. Especially we can see from the stacked spectra. So we can see there is a measurement, although with large uncertainty. So there's a measurement at redshift 6.2, and this is consistent with the best fit evolution model from our lemma alpha measurement. And to high redshift, still large scatter and over the limit. That's maybe affected by the small sample size at the high redshift end, and also affected by the high redshift transformation spike. I will show it later. So here we still need a larger sample at high redshift to constrain the lemma beta forest. And in addition to the lemma alpha and lemma beta forest, I'm also using the high redshift transmission spikes from our sightlines to identify our high redshift transmission spikes. We built up a sample of more than 400 transmission spikes at redshift higher than 5.5 to redshift up to 6.3, including lemma alpha and the lemma beta transmission spikes as shown in this figure. And since we already built a large sample, and we can do something statistical. And this is the bottom left one. This is number density evolution of this transmission spike. That's the number density along the sight line. So you can see the number density evolution over redshift, and also at different bins of the transmission spike strings. And we can see the obvious rapid decline with increasing redshift, and also with increasing transmission spike strings. So this evolution may suggest that there is a very rapid last transition phase of the reionization. And again, use this transmission spike back to the lemma alpha effective optical depth plot. We can also use these transmission spikes to constrain lemma alpha optical depth. So by assuming that this transmission spikes can represent the overflux from this sight line, which means that other pixels just have the zero fluxes. So we treat these two values as upper limit of the lemma alpha effective optical depth. You can see the open black squares here. There are the two upper limit from transmission spikes. You can see they have very good agreement with the best evolution model from the lemma alpha measurement. So this also can support that our transmission spike sample has a very high completeness. So the discovery of this transmission spike may suggest that a redshift around 6.2 to 6.3, the IGM may be already ionized. So there should be a rapid last transition phase of the reionization from redshift 7 to this redshift. And this is the first project using 3 different tracers to constrain the lemma alpha optical depths around redshift 6. And the next one is when we go to high redshift, when we want to go to redshift above 7, we can now see, we can now use the lemma alpha lemma beta forest, and also it's hard to find transmission spike there. So what we can use is a Quasar damping wing. as I showed before, there are already two quasars above redshift 7 have similar measurements. And these two quasars, these two new sightlines from our new survey is a redshift 7.5 quasar and a redshift 7 quasar. So we can see, interestingly, these two quasars give us very suppressed result because there's a very weak damping wing feature at redshift 7.5, but a very strong damping wing absorption at redshift around 7. So actually the redshift 7.5 sightline, the weak damping wing feature, that is more weaker than all of the other three quasars at redshift above 7 that have similar measurements. So the weak damping wing features could result in the discrepancy of the damping wing absorption features between these two sightlines result in the discrepancy of the neutral hydrogen fraction estimate. So in this figure, we can see this figure shows over the measurement of the neutral fraction from the high redshift quasars. So we can see including that's the low redshift one from the optical depth and all the dark gaps, and this 4 from 4 sightline for quasar sightline above redshift 7 as a damping wing measurement. So we can see from our two new sightlines, the orange point and also the red point. So then we get a high neutral fraction at redshift around 7 and a lower redshift neutral fraction at redshift around 7.5. So we can see, although they have the large uncertainty, but we can conclude that the discrepancy of the damping wing absorption features from these 4 quasar sightlines suggests that the realization could be patchy. Okay, and this is a summary. Yeah, we used our new quasar sample, a new quasar sample at redshift 6.3 to redshift 7.5 to constrain the IGM evolution, and including to project the first one is optical depth at redshift 6 and above, and the other one is the quasar damping wing at redshift higher than 7. Yeah, okay. I'll just leave it here and take questions. Thank you.
Thank you, Jinyi. So we've got questions on Slack already. So let me start with a question from Gabor Warszek, who asks, how do you combine sightlines of different data quality?
Sorry, just again,
How did you combine sightlines with different data quality?
It's just I combined the do you mean the stack spectral, the step of the stacking spectral?
I think
I guess yes. Yeah. We just stack the transmission spec, and they're from the different resolution and they have different signals. But I think the different resolution will just skew over the spectral to the lowest one in this bin. And we just stack the histogram, stack the pixels within this bin, and get a stack of the 1D transmission spectral, and then get a stacked spectral of the over 1D transmission spectrals. Yeah, we're stacking the transmitted flux.
Yeah. So a question from Hamza Padmanabhan, who asks, in your effective optical depth plot, is the dotted line an extrapolation from the FAN 2006 results? If so, it seems to indicate a rapid evolution in tau effective. Has the scatter actually decreased with the new sample, comparing the left and right curves?
Do you mean the dotted line? I think I mean the dotted line here. I think, yeah, the dotted line is from the FAN 2006. Yeah. Yes. And if so, it seems to indicate a rapid evolution. With the left and right curves.
And whether the new sample.
I need to back into this one. I think
whether the scatter is decreased in the new sample.
I don't think the scatter is decreasing. Actually, as I mentioned before, the scatter redshift around 5.5 and to redshift around 6 is consistent with previous studies that there is a large scatter. And to high redshift, the scatter is larger. But to high redshift, that may be affected by data quality. As we can see, there are around a lot of lower limits. Yeah. So the scatter is still large. It's not decreased.
Okay. Thanks. And then just one final question from Fahad Nazir, who asks, how are you dealing with the continuum correction of these high redshifts, as these sightlines can be affected by variations and troughs?
I think you mean the continuum fitting of the intrinsic intrinsic quasar spectral. Currently, we only have the optical spectra. So this is a very high redshift quasar sample. So we just typically just only have lemma alpha and negative 5 line. So we cannot do PCA. So I'm just using a power law. And the uncertainty of the power law fitting is around 10% to 15%. Yes, there is a, but actually I did some comparison. Our result, for example, we know the Atlas 2018, they're using the PCA model. And I can show you also this one. That one may be more interesting. I just compare our result to the distribution of the lemma effective depths, and to compare our result with previous studies. So we can see our result, the right line is consistent with the previous studies within uncertainty. Although some of the previous studies are using PCA, some of them are using the power law fitting. So that may be support that the power law uncertainty will not significantly change the result. Yeah.
Thank you. So it looks like, unfortunately, Michaela wasn't able to connect to this session. So Michaela Bagley is going to record her talk and it will be posted online. So please do check that out and ask questions in Slack. And we should be able to link, I guess we can link to it within the Slack channel for this session as well.